Welcome, everyone. Sorry, there are some technical difficulties, like all the virtual events. So now we are getting things started. And welcome to our sixth plenary session of this workshop, day 4. It's getting close to the end. And today, we're going to focusing on the emerging technology for the NOAA missions. Before we get into the meat of the session today, we want to remind everyone the code of conduct for the events, that we want everyone to make sure this workshop is a safe, productive, inclusive, and welcoming environment. So if you encounter any activities that's not acceptable, please let the workshop planning team know at ai.workshop@noaa.gov. And as a reminder, we're going to use Slido for all the plenary sessions. If you can go to the link slido.com, enter code NOAA 2021. That will be the place you'll submit your questions, and we will get to your question at the end of the session, or you can just use the link that we're going to share in the chat shortly. And with that, I would like to introduce Dr. Eric King, who is a co-chair for the workshop, to kick off this session.
Thank you, Douglas. Thanks for the introduction. Yeah, this is session 6. Welcome to session 6 of our plenaries. We've had some fantastic plenaries, really exceeded expectations, set wonderful tone for the meeting across the few days, and I'm looking forward to this one as well. Our plenaries have been focused broadly on AI and environmental sciences, and now since this is a NOAA workshop, I guess we're getting down to the reality of how does AI benefit the NOAA mission. So we're going to go across the NOAA mission space from weather and climate to space weather to oceans with 3 speakers. Our first group that will be speaking is Amy McGovern and Jason Hickey. Why don't you guys begin, and I will warn you at 2 minutes of your 25-minute talk. Thank you.
Okay, can you see that all fine?
Looks good.
Okay, I really wish Zoom didn't do the full screen and you can't see anything mode. Okay, so we are going to start. What we were asked to talk about was the future of AI. So we're going to talk about the decadal vision of AI and weather and climate research. So I'm Amy McGovern. I'm at the University of Oklahoma. I'm also visiting faculty at Google Research right now. And it's Jason's turn to introduce himself.
And I'm Jason Hickey. I'm the lead for AI for weather and climate in Google Research. And we're going to talk about the forecast for forecasting.
Which, by the way, is going to be a fun discussion. I like that pun. So when asked to talk about the decadal future of AI and machine learning for weather and climate, we first drew upon the ECMWF roadmap that recently came out. This is from Peter Dubin. And in that roadmap, they say that they anticipate that it will be increasingly difficult to distinguish between scientists working on machine learning and domain scientists in the future. It will be no longer possible to identify the tools that were originally targeted for machine learning applications in 10 years. This is an ambitious vision, and I think it's really, really interesting. And the question is, they have a roadmap and a plan for ECMWF and for Europe. Our question that we wanted to answer is, how can the US weather enterprise achieve this? So our next slide, I promise this is the only super wordy slide that we have, but we wanted to really actually write down a decadal vision and then spend a fair amount of time talking about it. So I in general, do not like to make super wordy slides and talk about them, but this one we felt like it was really important. And so Jason and I are going to talk about different parts of it alternatingly. So thinking about 10 years from now, we are thinking the same sort of vision as the ECMWF vision, but AI and machine learning is going to be fully integrated into the weather, water, and climate enterprise. And from here on, to make it shorter, we go with WWC, spanning from all the way from foundational research to operations. We're going to revolutionize our scientific understanding. We're going to facilitate and do this by facilitating exploration and creation of large, detailed, accurate models. And at this point, I will point you to the picture we put on the right-hand side, because this is actually the same picture that Peter talked about yesterday. This is the digital twin. This is a 1 kilometer resolution model that the ECMWF is developing. And as Peter said yesterday, it's your guess to figure out which side of that model is the model and which side is actually the observations. The idea is that eventually there'll be a 1 kilometer global scale simulation system that is a twin of the Earth, and that you can do very accurate simulations. And this is going to revolutionize what we're going to be able to do. We're going to seamlessly integrate AI into forecasting at all scales. So from the micro scale all the way up to the climate scale. And we're going to facilitate scientific discovery and forecast improvement. So we're not talking about just forecasting the forecast and improving the forecast, but we want to facilitate new knowledge discovery as well. And Jason and I were going to split this slide. Jason, did you want the second half?
Sure. And I think, so we have these scientific goals that Amy has described, but it's also important to think about how this is going to be used. What is the world going to look like 10 years from now? What do we want it to look like? And I think that we'll see an increasing level of accuracy in our forecasts that can be utilized by corporations and organizations of many different kinds. But we'll also see an increasing personalization of the weather. So you can imagine weather information informing your self-driving car, or telling you when is the best time to go jogging, or warning you of extreme events that to allow you to make effective decisions about how you're going to manage your life. And so this is not only a scientific endeavor, but it stretches all the way from the forecasting technology through the delivery to the end user of all different kinds of individuals, as well as organizations and governments and so on.
And in that second paragraph in the second discussion that Jason's talking about, one of the things we wanted to emphasize is that by looking at this future of what AI is going to do, we're transforming our relationship with the world by creating this digital twin, by creating personalizations that can be used by corporations and by individuals. We're really transforming our relationship with the weather and the climate around us, and hopefully transforming our understanding as well. And I don't want to lose that last point as well, which is that on the very last paragraph there,
yeah,
everything we're talking about so far has been very technically focused. In order to do everything we're talking about, we need to do this through true deep collaborations with social scientists, because we need to understand what it means to change our relationship with the weather and the climate scale. We need to understand how we can do things in a personalized way that actually improves decision-making and communication. And that is going to be critical to making sure that we actually achieve this vision.
Right. And yeah, to add to that, I mean, this requires engagement from all different parts of the weather enterprise, all the way from the forecasting technology and the production of forecasts to delivery in a way that is effective and communicate risk effectively.
So we talked about, we wrote this bold vision, and the question is, how are we going to achieve this vision? And there are two ways we could talk about this vision, and we're briefly going to talk about the technical aspects. And the reason that we're going to focus only briefly on the technical aspects is that we feel that there's a fair amount of research already being done on the technical aspects, and that the policy and the platforms that we need to change are what we really need to focus on to make this actually happen in the next 10 years. So we're going to break the next part of the talk into these two sections, the technical aspects and the policy and platforms, but we're going to spend the majority of the time on policy and platforms. So I'm going to start with the technical aspects, and apologies right up front to anybody whose group I missed. I thought I'm going to put a set of logos on here, and then I went, this is crazy. I'm going to piss off a whole bunch of people. I did it anyway. So if your group isn't there, I didn't mean to make you mad. I just grabbed a bunch of logos of people that were very large scale efforts that are working on improving AI and machine learning forecasting over the next decade. And so it's just a very large set of people. What we're thinking is that there's a list of things that we need to do. And we started making a list, and we said we could spend all 25 minutes of our talk on this, and we don't want to do that because that's not where we want to go. Yes, we need substantial advances in AI and machine learning. We need to improve trustworthy AI. That's what our center is on. We need to improve uncertainty quantification, robustness of the AI, physics-informed AI, ethical and responsible AI. We need to make sure everything we're doing is actually ethical and responsible, that what we're doing creates environmental justice and does not perpetuate environmental injustice. This list could go on. I didn't even list the things for climate, for example. And NSF just invested $25 million in an AI-based climate modeling center at Columbia. I went to grab their logo, and I ended up with a news story because they're so brand new. They literally started last week, that they didn't have a logo yet. This is clearly an effort that there's a lot of money being held at the federal level, being invested at the federal level in improving AI for environmental sciences and earth sciences. And so we believe that for the sake of this talk, let's just assume that all of these efforts are going to succeed, and let's focus more on the things that we know that really need to be changed. Although I will say, if there's federal people listening, I believe that more money invested in all of this is still critically important, and I'm not saying that's not the case.
it's also important to consider the role of HPC. So one completely wonderful thing about the area that we work in is that it's data rich. We have a lot of observations, we have model outputs, we have very large data sets, different kinds. Of course, there's widely varying qualities in these data sets. They come in different formats and different shapes and so on, but we have a lot of data. The diagram at the upper right is from Peter Dubin's talk yesterday from ECMWF, showing the ways, the opportunities that we can use AI. And if you look at the bottom right, this is Lior, a 1 meter simulation of a tornado. This is a vast amount of data. It's a wonderful source of information. How are we going to learn this? How can we use this data set to inform machine learning? Also at the bottom, we see the projected growth of data of the NOAA archive reaching 30 or so petabytes by 2030. I would actually say this is probably an underestimate of the archive size. We have increasing number of data sets and increasing resolution. And so how are we going to use this? How are we going to develop models? Of course, we want HPC for numerical methods, but we also need the HPC support to process these very large scale data sets using machine learning. And these require large platforms. Now, one thing that we haven't seen, which it seems inevitable, is very large machine learning models. So if you look in the language space, GPT-3 is up around 10 to 11 parameters. These are huge models that are great at conversational AI. And these kinds of models have yet to be tried in the weather domain, to my knowledge. And we would like to apply these methods. This is a perfect domain for applying these methods. And what we need is the platforms to support these investigations. So another issue that we're currently facing is that the domain is very heavily siloed. So many of our research groups, academic and industry and even government research groups, rely on a download and process model. So we download the data, particularly from NOAA, we download it to our local site, and then we process it locally using our local platforms. So this limits the kinds of collaborations that we can participate in. And it also limits the supply of knowledge. Now, there is an open science movement based on open source platforms that provide a variety of tools to address these problems. Cloud optimized data sets like XAR that allow us to store data in a common representation, common usable representation on cloud, Xarray, Pandas, Pangeo, and tools to process and analyze the data to build machine learning models. And we have accessible cloud platforms. Now, all these tools are in development and currently are on the way to supporting a unified ecosystem, but the ecosystem is not there yet. We need a common plan for cloud platforms, for data representations, for data sharing, for model sharing, for reproducibility, and so on. I'll talk more about environmental justice. I see this as increasing the utility of our scientific effort, but also supporting uniform access to all populations. And this is a cornerstone for environmental justice. Next slide.
Before I move it to the next slide, I would add that this and the previous slide go together as well while we're talking about the open source movement and the open science movement that is also relates to the HPC needs that we talked about.
Yeah, good. Okay, and so we see large scale efforts in this direction. So Peter Dubin talked about the 10-year roadmap for ECMWF for ML. The digital twin is a platform that unifies multiple parts of the European efforts, provides a common platform for the European efforts. We see multiple strategies that are being supported by NOAA around cloud, around data, around artificial intelligence, and these are all in support of this effort. And we also see crises. For instance, the scalability of our information dissemination products. I mean, this has been a problem that when we have extreme weather events and our tools are most important, we are reaching scalability limits and the system is crashing. So this is exactly what we don't want to do. We want our system to be robust, especially during extreme events. So we see multiple efforts moving in this direction, crises that are also pushing us in that direction as well. Okay, and next one. And I want to talk about environmental justice. So as our climate changes, the effects of the climate of extreme events affect many different parts of the world, but disproportionately affect areas of the world that are traditionally underserved. If we want to address this, we need to move out of the siloed mindset. We need to move out of the world where weather forecasting and the technology for weather forecasting is maintained by a few individual organizations that have primary access to that information. If we want to address this, we would like this weather and forecasting products and the technology to be available to all. There are many other reasons why we want to do that as well. So if we have open platforms, then we can have an extended workforce. We can have a mobile workforce and a distributed workforce. So it also leads to, supports the acquisition of talent and training and so on. But especially we want to have our ecosystem, the entire ecosystem around weather and climate and forecasting and the technology and machine learning to be as open as possible and as transparent as possible.
And that includes both the data we talked about before, but also the HPC, because we know that it is part of the environmental justice and allowing it to be available to everybody if everybody can actually access the resources they need to do the machine learning training.
Mm-hmm.
I think this slide is mine.
I think so.
we went through beforehand and said which numbers were which, and then the slides don't have numbers on them, so I can't see them in full screen mode. Yeah. So the next part of the policies, and remember we've moved from our outline from the technical part to the policies that need to be shifted, is that we need to create a new paradigm for making multi-sector partnerships. Jason and I actually had a talk on Tuesday, so you can see it in our recorded version of the talk on Tuesday about why we need a new paradigm for multi-sector partnerships. So I'm just going to briefly do this just in case you didn't see the talk. So very, very short. Multi-sector partnerships across government, industry, and academia are really valuable. We're leveraging different kinds of expertise, and we're getting much more creativity because each one of the different sectors has a very different perspective and they have very different needs, and their needs can drive each other's development. So for example, knowing what is needed for operations might drive the fundamental research, or there may be something in foundational research that needs to be transferred to operations that, without the partnership, really there's sort of a gulf there that can't be done. And so we need to be able to create these multi-sector partnerships, but they're not just as easy as saying, hey, let's go make this partnership. And Jason and I talked about that on Tuesday, about all the ways in which the partnerships can go wrong right now under the current paradigms. We need to find ways that will facilitate rapid innovation, and R2X is it's not just R2O, it's research transferred to all sorts of different end users. One of the biggest ones that holds us up is that the different sectors have different IP, intellectual property. And so we need to find a creative, innovative way to make all of the lawyers happy, if that's a possibility, that will actually create innovation. So I'm gonna leave it there and say, go see our talk on Tuesday to talk more about that. But I really, really think this is key to achieving our decadal vision, because if we all continue in our own little sector, doing our own thing, we're not going to achieve what we want to do in the next 10 years. I don't remember which slide we switch on, so tell me, Jason.
I think this is for you, actually.
Okay. Yeah. So the next thing we need to talk about, and this has been a lot of the focus of this conference in the sense that we're all trying to talk about the machine learning and the AI, we really need to talk about how we can retrain our workforce. So when we're talking and I'm going to speak from the academic side, I can talk about how to retrain my students and how to change the curriculum, but there's a lot of workforce out there that needs to be retrained, and they're not just going to go back to school and get a new degree. That's unfeasible to ask them to do that. So we need to develop a lot of flexible options that can train people up on the machine learning. And this needs to be not just, here's this line in Python that you can use. We need to have a foundational understanding of the method. If we're going to choose, I chose this quote, actually, Jason and I met with Peter last week to talk about these slides and to see if Peter had any ideas, since he had the ECMWF vision. And he had a quote that I liked, and I put into here, that machine learning is just another tool in the toolbox. So if machine learning is really just another tool in the toolbox, then in order for it to really become indistinguishable, so that a scientist can just grab a method, they need to really understand why they choose a method, which method they should choose, how to apply it to the problem at hand, and how it might need to be adjusted. And right now, I don't think that our training is focusing on that. I think a lot of our training is very surface level. Here's what a tree is, and here's how the lines of code you should use to do it. Here's a neural net, and here's the lines of code you should use to do it. People don't understand why they might want to choose one or the other. And as an editor, I see this because we get papers in that come in with, this is just a shiny new tool, but it really isn't the right tool for the problem. So if we're going to use this to foundationally change the science, then the scientists really need to understand what method they should use, why, and how to innovate. And I would push that, sometimes I get pushback when I try to talk about this. The weather and climate workforce have the math background. Every single one that I've ever met, y'all learn a lot of math. Remember, my training's in computer science. We learn a fair amount of math too, but meteorologists learn a lot of math. You can understand the machine learning. Often what's lacking is the programming experience, especially for the more current workforce, because academia is adding more programming in. And so we need to work on getting that up as well. But on the CS side, for the AI people, they don't have the training in the physics. And they really need the training in the physical nature of the domain scientists so that they don't blindly take the shiny new hammer and try to apply it and do something very wrong. And this pushes me to the next one, which I know is my slide, because what we really need to do inside academia is develop new educational approaches to training this. So I gave a talk at AMS a couple of years ago. Actually, if anybody was there, I landed a drone in my hand, if you remember that talk, talking about how we needed new paradigms for what I called physical data scientists, where we actually merge the training for all of these disciplines together. There will be a paper coming out in EOS sometime in the next few weeks. It's in final processing with the editors that talks about how this should work, how we can create a new training paradigm inside academia to create innovation in AI, specifically for weather, water, and climate. I think this was you, Jason.
Yeah, so actually, one thing I want to add to what you just said, Amy, we're at a really wonderful time in the course of environmental science, where we have vast amounts of data. It's publicly available. This is actually accessible on cloud platforms, so that anyone at the moment, anyone in the world can make a weather forecast, can just log onto the cloud, build a model, train it against the data that we have, and produce a forecast from that. So we're in a really wonderful situation where the tools are not isolated. We can use these for training. We can use these for supporting our students, and also making progress and drawing in creativity from throughout the world to address problems that are really important. So we are at a phase in time where the challenges are really quite large, and we want to utilize that creativity as much as possible. Also, we need cooperation. We want cooperation throughout the weather enterprise. Some examples that I'm thinking of being at Google, we have, for example, a flood forecasting effort where we do build models, but we cooperate with national agencies to issue alerts. The one advantage of the Google platform is that there's extensive reach, so we can reach nearly everybody in the world. But this needs to be done in partnership with a government organization that's responsible for the forecasting and the alerts. And I see this as an example of the development of innovative products. I talked earlier about personalized weather forecasts that you use for your cars, you use for agriculture, you use for managing your schedule, you use it for routing. This is also, of course, usable for things like logistics and so on. These personalized weather applications provide targeted decision making, give you the ability to interact with the information that you're receiving and make effective decisions. And this is not limited to a single sector. So we need cooperation from all sectors, from academia, from the government and private industry, to provide this kind of extensive information platform that can be used to improve the quality of life, both for extreme events, but also for the normal, mundane, everyday events, like, is it going to be hot today? Is it going to be cold? Is it going to be rainy? And allow me to make, or anyone to make decisions around their life. Okay, what? So we have the personalized weather applications, and of course we have these targeted use cases. Right. I think
you got everything on this slide.
Okay, good. Yeah.
And I think that's actually our last slide. So because I'm funded by NSF, that my very last slide is that I have to have my acknowledgement of my funding. So we are glad to take questions. I don't know, because we started a few minutes late, I actually have no idea where we are on timing. So Douglas or Eric will have to tell us.
Your timing was perfect, guys, within 20 seconds of your allotted time. So really good job. We are getting questions. To remind the audience, there's questions in the Slido, which we'll address with each group afterwards. And don't forget to put in your favorite questions or upvote them. Thank you guys for setting a great tone there. It was really important to remind ourselves that technically we have a lot of progress being made and a lot of good forward momentum, but really a lot of the challenges in this are societal and social sciences based, that how we're going to make use of this, how we're going to bring equity and inclusion to it. So I really appreciate that as setting the tone. We'll move on to our next speaker, Christin, if you're ready. She'll be talking about deep blue learning and how that's being used in NOAA Fisheries. And I would be remiss if I did not tell you that Fisheries has really been leading the way in the adoption of AI in NOAA, at least as far as getting it into operations, pushing it through their science council. They've gotten a lot of great different applications into operations. So I'm really excited to hear this. Christin, the floor is yours.
Hi there. Can you see my slides?
Got them.
Okay, I don't see them, but I'll take your word for it. My name is Christin, and I'm a biologist at the NOAA Northeast Fisheries Science Center in Woods Hole. And I'm really thrilled to have this opportunity to share with you my vision for how AI can transform the future of NOAA fisheries. I'll start with a little bit of background and what led me to dive into AI, and then highlight some other really awesome work being done in the fisheries, touch on our new project to detect animals from space. And finally, I just want to share with you my enthusiasm for the future of AI and how we can dive even deeper. So we'll start with how a data science competition turned a biologist into an AI project manager. My bachelor's from Northeastern University was in biology, and my master's at San Francisco State focused on the development of vocalizations in harbor seals. In 2005, I found myself flying in a small airplane off the coast of Georgia looking for right whales, and I just loved this work so much that it's what I've been doing ever since. These aerial surveys fly a set of track lines searching for and photographing right whales to feed into our understanding of their abundance and distribution. On days that we are lucky enough to find and photograph right whales, those images are then matched against the photo identification catalog curated by the New England Aquarium. Sometimes identifying these whales is super easy, and there are individuals that we can recognize even from an airplane miles away, like Ruffian, who has very distinctive scar patterns. But for whales with very generic velocities, bad photographs, and limited sighting records, well, sometimes it can be really quite frustrating. One such day, I took a break from matching whales and distracted myself on Facebook. I was immediately greeted by the suggestion that I might want to tag myself in a photograph. This got the gears churning as I thought with exasperation, no, I don't need help recognizing myself, but could you help me with this whale? So after bouncing the idea around for a while, a colleague of mine suggested a Kaggle competition for algorithm development. Now, I imagine by now you're all quite familiar with the concept of a data science competition, where citizen scientists from around the world compete to help solve your problems. Well, back in 2015, the idea was fairly new to me, and I was really stunned by the ease of harnessing such a high-quality talent pool to tackle my challenging problem. The effort was tremendously successful, And in the end, 364 teams of data scientists participated. It became clear that the best solutions to this problem were based on convolutional neural networks, which is not something that I knew before this competition. And we achieved a percent correct classification score of 87%. And we received the source code on GitHub. I went on to collaborate with the winning team, NCAI, to publish the results of their deep learning approach in an attempt to encourage others to consider AI approaches for photo ID. But going from the success of a technical solution to the user-friendly interface that I really needed turned out to be a much bigger challenge than I had originally anticipated. And it took a while to both figure out and fund the ideal solution. Eventually, I found success by collaborating with the team from WildMe, the developers of Flipbook. It turns out I didn't actually have to reinvent the wheel, and they already had laid a lot of the groundwork on a user-friendly platform built for applying AI to photo identification. The system was originally designed for whale sharks, but has since expanded to include many other species. So even though WildMe had their own existing algorithms, they were willing to collaborate and incorporate this new deep learning algorithm for right whales into their code base. And the team from NCAI, who won the Kaggle competition, was willing to provide technical support to assist during their first attempt at retraining the algorithm. So it was really the best of both worlds. The system finally went live for North Atlantic right whales in 2019. The New England Aquarium was engaged as an important partner in this effort, and we found a way to seamlessly integrate this new AI system through the existing North Atlantic right whale catalog website. North Atlantic right whales are morphologically similar to the southern right whale. And while initially I was a bit daunted by the challenge of incorporating these other photo ID catalogs, the benefits to the research community were just too great to ignore. So in 2020, we expanded the system to include catalogs from South Africa, New Zealand, Australia, Argentina, Brazil, and Chile. In 2020, machine learning was completed to expand the capacity of the system to also be able to recognize whales from lateral-based photographs. Previously, it only worked on overhead photos taken from an aircraft. And WildMe really achieved some impressive results on these challenging images using background subtraction and a state-of-the-art machine learning algorithm named Pi for pose invariant embeddings. This novel approach is achieving 55% top 1 accuracy and 80% top 5 accuracy on truly messy real-world data, I will add, if that doesn't sound impressive. This work to be able to match whales based on multiple features and from multiple perspectives is really pushing the boundary on what is possible in automated wildlife identification. So while there is still lots of room for improvement in the system, we now have an operational AI-based workflow for the detection of right whales from both aircraft and vessel photos. And we're even beta testing a system where a photo can be quickly submitted and ID'd using Twitter. This project was only possible through extensive collaboration, and I have many folks to thank for their open minds and collaborative spirit. I think we've heard a lot during this workshop on whether we should train domain experts in machine learning or train the machine learning experts in the domain expertise. And I would argue that you really need both. This broad collaboration is really the best way to make things happen and make sure that you don't miss anything important. NOAA scientists across the agency are breaking ground on similar projects to harness the power of AI to better understand the world's oceans. By now, you're all familiar with the development of Viame. This is the first automated image recognition software using advanced computer vision and machine learning technology for the marine environment. Scientific programs across NOAA have begun using the toolkit for the annotation and detection of marine species. Katie Sweeney at the Marine Mammal Laboratory is using Viame to automate image processing and analysis of the Steller sea lion aerial surveys. This is expected to reduce effort by 80% over manual counting methods. Another marine mammal lab scientist, Erin Moreland, is using Viame and camera for real-time onboard processing of multispectral imagery. Hotspot detection from a YOLO model run against infrared imagery triggers further processing of color imagery to detect and classify ring seals, bearded seals, and polar bears. And Erin is really leading the charge on edge computing. Her level of ambition with what she's trying to do with this project is mind-blowing. So if you're looking to learn more about edge processing, she's the one to talk to. At the Pacific Islands Fisheries Science Center, Ben Richards and his team of video analysts typically spend 3 to 4 months processing optical data from the annual Deep 7 bottom fish survey. To date, MaxN has really been the only tenable annotation method, and automated processing will greatly reduce processing time, allow for alternative enumeration methods such as mean count, and will really improve consistency and repeatability across annotation periods. At the Northeast Fisheries Science Center, Devora Hart is leading the annotation and machine learning development efforts using Viame to detect various species from the HabCam imagery: sea scallops, cancer crabs, wave whelks, and various classes of demersal fish. Future work includes developing annotators for more benthic invertebrates such as sea stars, anemones, sand dollars, and diazoans. At the Southwest Fisheries Science Center, Trevor Joyce and his colleagues, with support from the West Coast Regional Office and BOEM, are exploring the feasibility of using existing machine learning algorithms to partially automate the photo identification of gray whales within Fleetbook. Early results indicate that hotspotter and PI algorithms are promising for gray whales, and efforts are underway to further improve the algorithm performance. Manuel Castellote at the Alaska Fisheries Science Center is collaborating with Microsoft Teams AI for Earth and AI for Good to develop deep learning models to detect and classify vocalizations of the Cook Inlet beluga. These machine learning models enhance the team's speed and performance in processing large volumes of acoustic data. Matthew Campbell and Jack Pryor at the Southeast Fisheries Science Center are applying Viame to the CMAP and Reef Fish video survey in order to detect, identify, and count species. Several iterations of machine learning models have been developed, along with a large library of annotations that includes over 130 classes. Also at the Southeast Fisheries Science Center, Victoria Hermanson, Jeff Hickey, and George Cutter are working towards automated analysis of animal-borne video imagery to inform ecosystem-based fisheries management for the Southern Ocean fisheries. This imagery provides a predator's perspective to help quantify predation rates and really understand the functional response to variation in prey densities encountered while foraging. Every NOAA Science Center is exploring how AI can transform our work to be more efficient and effective. My own thoughts are consumed these days with the concept that someday, not soon, we could dramatically increase our understanding of marine mammals worldwide if we could build an operational pipeline for the automated detection and classification from very high resolution satellite imagery. Satellite detection of whales has been demonstrated as a proof of concept by several publications, most notably this recent work by Dr. Hannah Cubanes in 2018, which demonstrates the detection of 4 different species of whales: fin, humpback, right, and gray, from Maxar's WorldView 3 imagery with 31 centimeter panchromatic resolution. The 2019 paper by Alex Borowitz showed the ability to detect whales using convolutional neural networks using ResNet and DenseNet architecture on downsampled aerial images of minke whales and then tested on WorldView 3 imagery. This is really an exciting development because obviously machine learning algorithms are a precursor to any kind of a meaningful operational system. So all of this seminal research has been building up over the years into something that is beginning to look like we could take it out of academia and into production. At the last Marine Mammal Conference in Barcelona, there was a workshop on the detection of marine mammals from very high resolution satellite imagery. And the room was just abuzz with the possibilities that this holds for understanding worldwide marine mammal distribution and abundance someday. Another thing that really caught my attention is the initiative by the satellite company Maxar, the Worldview Legion program, which launches next year, and it will have a revisit rate of up to 15 times per day, and the capacity to collect more data over open water at that same 30-centimeter resolution as Worldview 3. In other words, there's a truly impressive scale of image collection just on the horizon. Because it's kind of fun to do the impossible, so I decided to dive in. So for the past year and a half or so, I've been building our network of collaborators. It's certainly going to take a village to fulfill this ambitious vision of creating a near real-time operational system to detect marine mammals with satellite imagery. Working closely with Kim Getz at the Alaska Fisheries Science Center, Kim White at BOEM, and Erin Murnane at the Naval Research Laboratory, we've been learning everything we can about satellite imagery and how to fit the pieces together to create an AI-powered cloud processing workflow. We decided to name our new initiative Gaia for Geospatial Artificial Intelligence for Animals. We have collected a tremendous volume of imagery from very high resolution satellites over seasonal hotspots of the North Atlantic right whale and the Cook Inlet beluga whale. And we have partnered with the private sector to bring in some much needed expertise. The team at the British Antarctic Survey has been breaking ground on satellite detection of animals ever since Fretwell's seminal publication in 2009, where he demonstrated that it was possible to detect penguins from space. Dr. Hannah Cubanes, a very accomplished and well-published researcher in this area, just received a grant from the Marine Mammal Commission to help us with the development of manual annotation protocols, and Penny Clark is volunteering her time on our project while she pursues her PhD. We received a grant from the Microsoft AI for Earth program for cloud computing resources and machine learning development. And Caleb Robinson there has already made some big contributions to the project with an automated batch processing routine for Brovie pan sharpening and an early machine learning non-water detection model. We are working closely with the satellite company Maxar to do large volume annotation campaign with their crowdsourcing platform GeoHive and their development team from XLabs, who will run some custom algorithms to make our crowdsourcing effort more efficient. So we have an amazing team in place and a solid plan for moving forward. But as we all know, things don't go according to plan. So we are anticipating a few bumps on the road along the way, perhaps a sea monster or two, and we will just do the best we can and keep moving forward. Because the biggest risk really is not taking any risks at all. So how can NOAA dive even deeper? Well, we have heard about so many groundbreaking projects happening in NOAA Fisheries, even now. The field of machine learning is truly in its infancy, and we're just beginning to scratch the surface on what is possible. While the general concept of AI has been around since ancient mythology, but AI research didn't even begin as an academic discipline until the 1950s, with computers that could play checkers, do algebra, and speak English. In 1957, the perceptron was born, originally planned as a machine, not a program. The Mark I perceptron was the first successful neurocomputer. In 1959, Arthur Samuel first coined the phrase machine learning, And in 1967, the nearest neighbor algorithm was the beginning of basic pattern recognition. The discovery and use of multi-layers, backpropagation, and artificial neural networks continued to push the field forward. And in 1990, the concept of boosting was first introduced. It was only in 2012 that the groundbreaking work on ImageNet led to a flurry of progress in convolutional neural networks. 2012 is really not very. This graph shows an increase in publications on machine learning and AI through 2018. And you can see the exponential growth in academic research on this topic. You can only imagine what it looks like today. This is just the beginning. Imagine what we can learn by applying machine learning to our understanding of the world's oceans. Can we really build an operational near real-time system for the identification and classification of marine animals from satellite imagery? Can we build an operational near real-time system for the detection and classification of marine animals from our acoustic technology? Can we anticipate where animals will be before we ever see or hear them, like looking into a crystal ball? Elliot Hazen's group is already starting to do this. And most importantly, can we use AI to better protect the world's oceans? I encourage you all to dive where the water is deep and see how AI can transform our understanding of the oceans.
Oh, right. Thank you very much. Yeah, that was a wonderful survey of all that's being done across fisheries and a really great reminder of how NOAA can harvest technology from partners to apply to its mission broadly. So you didn't disappoint with the survey across all that we're doing in the blue economy. Thank you. I think we'll move on to our last speaker. Excited for this one. My background is in space physics. I came up as an atmospheric modeler, so I'm excited to hear about how AI is being applied to space weather. Certainly was kind of a dream back in the days when I was writing models. So Enrico Camporeale will be presenting on NOAA and the Space Weather Prediction Center. Take the floor. It's yours.
Okay, hello everybody. So my name is Enrico Camporeale. I work at CU Boulder and the NOAA Space Weather Prediction Center. So first of all, let me thank the organizers for this wonderful opportunity to talk about space weather. Obviously, space weather is not a major topic among the audience of this workshop. Nevertheless, it's one of the activities NOAA is responsible for. So I'm gonna spend the first few slides just to introduce space weather for the benefit of the people that are not familiar with the topic. And as usual, the best definition comes from Wikipedia. So space weather is a branch of space physics and aeronomy, or collectively called heliophysics, concerned with the time-varying condition within the solar system. So this includes the solar wind, the space surrounding the Earth, so the magnetosphere, ionosphere, thermosphere, and exosphere. And just for clarity, just to make sure, be on the same page about nomenclature, space physics means the study of plasma within the solar system, so not to be confused with astronomy nor astrophysics. And of course, aeronomy means the upper atmosphere, and I believe that's probably the region where the most overlap with atmospheric science happens. So there are many different phenomena within space weather. Some of them are not really completely understood. So this is the sort of the easy picture here. So Earth, this small dot here, is surrounded by a magnetic bubble called the magnetosphere. And that's actually the very reason why life is possible on our planet. However, this magnetosphere is bombarded continuously by particles and radiation. So the solar wind is a flow of energetic electrons and ions or plasma continuously being emitted by the sun. At times, the solar wind is more energetic. sometimes the sun emits this huge amount of plasma called coronal mass ejection. Other times there are solar flares, which are electromagnetic radiation. So all of these effects come into the way of the magnetosphere and perturb the geomagnetic field. So the sort of technological aspect of space weather is the following. You can very well imagine that when a satellite, the electronics on a satellite are bombarded by energetic ions and electrons, they might malfunction. There have been a few cases where satellites have been completely knocked out by space weather events. Then there are effects on the ionosphere, so GPS signal scintillation, disturbance in the GNSS, and effects on radiation effects on avionics, and eventually this perturbed magnetic field can induce geomagnetically induced current in power system, in electrical grid, and eventually produce blackouts. So of course it's always hard to make economic estimates of rare events such as space weather. Nevertheless, people have tried to do that in sort of a scientific manner. So now it is estimated that the cost to US electricity consumers by a space weather event, and again, these numbers I believe are in the right ballpark, although there's quite a range here. So this may be 400 million to 10 billion for a moderate event, or 1 billion to 20 billion for a more extreme event. So it is also estimated that the annual cost of adverse impact of space weather, it's between 200 and 400 million. Of course, if a satellite is lost, again, as it has happened in the past, even just to replace that single satellite might cost up to $200 million, and so on. So a big one, and I'm not sure what that means. I will explain what that means in a second. Actually, a big one is estimated to cause about 2.6 trillion in damage. And in our community, the big one means, so we have only one recorded event. It happened in 1860. In that case, at that time, the major technological impact was that the telegraph stopped working worldwide, and auroras were seen down to the Cuba, basically. So it was a very extraordinary event, and you can very well imagine what that would mean with all the satellites and the infrastructure we have today. So really, space weather, this is sort of the bottom line, is in my opinion, in many other people's opinion, is really a disaster waiting to happen. You can see that as a black swan, meaning that one single, very rare and very extreme event may be disruptive for our society. So as I said, NOAA, so here in Boulder, there's a Space Weather Prediction Center, or as we call it, SWIPSI. So SWIPSI mission is to safeguard society with actionable space weather information. So there's an office here where a forecaster is on duty 24/7. And this is the SWIPSI website where you can gather all sorts of information on nowcasting or forecasting of space weather events. So let's switch to machine learning in space weather. So let me start by saying that it is commonly said or believed that space weather prediction is around 50 years behind terrestrial weather predictions. And there are, now whether this is 50 years, 20 or 30 doesn't really matter, but there are some very good reasons for that. First of all, there is a lack of fundamental understanding. So it might very well be that plasma physics is actually 50 years behind fluidodynamics. The major difference, I believe, between space weather and meteorological weather is the sparsity of observations. So we take observations from satellites and from ground-based magnetometers, but these are very sparse, both in temporally and spatially. So we are nowhere near the abundance of data that we have in meteorology. Then finally, another, I think, major problem is a lack of standardization of metrics. And this is still a relatively new field, so it's still very often not quite clear what are the users' needs and so on. Nevertheless, if we look at the specific niche of machine learning within space weather, I think this is catching up rapidly. So it might be the case that within machine learning, we are only about 10 years behind terrestrial weather. So just as a statistic, in 2020, 7% of papers published in space weather journals used the machine learning. And you can see this is the growth of, so this is a search on this archive. If you look for space weather and machine learning, this is the number of publications, refereed and not refereed. So it's really just in the last 5 or 6 years that this topic really was starting to grow exponentially. So I'm going to go through a sort of quick list here of what can machine learning do for space weather. Of course, this is not at all a comprehensive list. So the first thing is the forecast of global or average indexes such as DST. And I think it's believed now in the community that machine learning works better than physics-based simulation to forecast indexes such as DST. So DST is what is called the disturbance storm time. It's an index it's a proxy for basically the magnetic activity, which is derived from a network of geomagnetic observatories close to the equator. And this is just an example of one of the major recorded storm in recent history. So the yellow line here is the observed DST. So this is your ground truth. The red line is the solution of a physics-based model called Geospace, which is operational at NOAA. And the blue line is the forecast from a machine learning model. In this case, it's a combination of neural network and Gaussian processes. So, of course, you can see that the machine learning is not perfect, but it's much better than the physics-based model. And the reason might be very simple. I mean, we are talking about a physics-based approach of a very complex system. In order to get this global index right, you may need to get every single piece right, which may be very difficult for a physics-based approach. Going on with other examples of machine learning in space weather, this is something which is quite successful, is the segmentation of solar disk images. So this can be done both in a supervised or unsupervised way. These are two different papers and approaches. So the idea here is to automatically, so this is a solar disk image, is to automatically extract different solar regions that are associated with different solar wind and different geoeffectiveness. Also, this will be a supervised example, solar wind classification. So this is a paper I published a few years back. We took a database which was labeled by humans that contain about 8,000 hours, so a bit less than 1 year. So the idea here is that solar wind comes in different forms and types, and you want to know which solar wind you have at any given time. So learning from this 1 year of data, we were able to label 40 plus years of data. On the other hand, you could also do solar wind classification with unsupervised methods, such as in this paper, where here the idea is you're trying to learn and understand what are the different kinds of solar wind, again, applying unsupervised methods. So this is, I won't go much into detail here, but it's just a list of regression problems which have been tackled in space weather. So I already mentioned the forecasting or predicting geomagnetic indices, forecasting the arrival time of this coronal mass ejection, this huge burst of plasma. This is an ionospheric application, the global TEC or total electron content maps, forecast of solar wind speed, relativistic electrons at geo, and so on. Then there are, of course, also classification problems within space weather. For instance, and these are all published papers. What is the probability that an active region on the sun will produce a flare in the next 24 hours? What is the probability that dBdt, which is the rate of change of the magnetic field on Earth, will exceed a given value. What is the probability that the solar wind originates by coronal holes, et cetera, et cetera. So I want to spend now a couple of minutes doing sort of a short digression. I'm not even sure this is needed for this audience, but I wanted to do it nevertheless, because especially talking with non-specialists, the question that always comes up is why does it work, and why does it work so well when we apply machine learning in physics? And so I want to start by this very famous essay published 60 years ago by the Nobel laureate Eugene Wigner on the unreasonable effectiveness of mathematics in the natural sciences. The question Wigner was posing was why math works so well to describe natural phenomena. And I think it's very fascinating, the concluding remark of this essay that says that the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. And following this sort of path in recent years, like 5 or 10 years ago, several papers have been published with similar titles about the unreasonable effectiveness of data, unreasonable effectiveness of deep learning. So again, the question is why deep learning or data-driven approaches work so well. The point I'm trying to make here is that we in space weather or in physics in general, we are not in the same boat with image and text recognition, self-driving, recommendation system, or many other ways machine learning is applied in industry. And the reason, of course, is that for us, physics, as always, or as often, comes to the rescue. So in other words, there are physical properties such as invariance, symmetry, conservation laws, and so on that reduce drastically the search space of parameters. If you think, for instance, in terms of neural networks. In fact, any system that follows the laws of physics, I think, should be learnable by machine learning. And I truly believe that any physics-based simulation, in fact, can be emulated by machine learning. Of course, the problem and the major hurdle is to have, the data quality and data quantities, to have enough data and good data. And this is an interesting paper that I recommend reading on why does deep and cheap learning work so well in physics, and basically it reiterates all of these points. So I promised in the title of my presentation to talk about some path forward for machine learning in space weather, and I believe, or I hope, so I'm going to show now in the next few minutes a few problems that I think need to be overcome, and I believe that some of those problems might actually be overlapping. Those are not specific to space weather, and I hope to get the interest also of atmospheric scientists, climate scientists. I believe that many of those problems are the same. So this list is sort of freely taken and adapted from this review paper on machine learning in space weather that I published a couple of years back. So the first problem is what I call the information problem, which is, what is the minimal physical information required to make a forecast? And this is a very clear example here. Of course, this again, it's applied to machine learning, to space weather in particular. So if we take solar images, we at any given time, we have access to 200 million pixels from different solar images, taken with different instruments and different wavelengths. Now, I'm sure, I think everybody in the community is well, maybe not everybody, the majority of people are sure that those images contain the information to forecast, for instance, solar wind speed or temperature. But then, of course, the problem is how, this is really a problem in machine learning, how you derive one single scalar value at any given time from 200 million points. So again, the information problem. The next problem is the gray box problem. So yesterday there was a talk from the UK Met Office where the word fusion was used. I like to call this the gray box approach. So what is the best way to make an optimal use of physical understanding and physics-based simulations and data-driven system? So this is a paper where we tried this gray box approach, and this is a nice example where this actually works. So what is shown here on vertical axis is the true skill statistics. This is a classification problem. So the closer you are to one, the more accurate your classifier is. And the yellow line here is the result of a white box, meaning a physics-based model. And this is a model which is operational again at SWIPSI. If we fly here, disturbing me. If we try a completely data-driven approach, so this is what I call a black box. Of course, you can improve this skill, but the best of both worlds comes with the gray box approach, where you combine both the physics-based model and the data-driven approach, and this gives you actually the largest score in this particular case.
Enrico, 2 minutes, please.
All right, so I'm gonna go real quick. The surrogate problem, what components in the space weather chain can be replaced by a black box surrogate? In this case, you have to trade off between loss of accuracy and speed up. The uncertainty problem, this is something I have worked quite a bit. I think it's very interesting and very important. In space weather, most of the services provide forecasts in terms of single point predictions. How do you assess and understand the uncertainties associated with those predictions? And to propagate those, it's very important and also computationally demanding, and machine learning can help in this. And those are 2 examples, 2 papers where we generated the probabilistic forecast from deterministic models. The too often, too quiet problem in space weather in particular, we are really interested in rare and extreme events. So this paper shows the occurrence of extreme.
Seems like we have lost Enrico. Eric, are you there?
I'm here. I don't see him either.
Enrico, are you back?
I am back. Did I drop out?
Yes, you dropped out.
Okay, sorry about that. Okay, I guess I'm just gonna jump to my conclusion. Can you still see my screen?
We are not seeing your screen right now.
Oh, sorry. I need to share again. Okay, I'm not sure where you lost me. I was talking about this. I'm just gonna jump to the conclusion. Do you see my screen now?
Yeah, if you could go to the conclusions, that'd be great.
Okay, just wanna mention this because I think it's very important and interesting for many of the people in the audience, is the knowledge discovery and explainability problem. So in other words, from a physicist point of view, how do we distill some knowledge from a machine learning model, and how do we improve our understanding of a given system? So in other words, how do we open the black box ML algorithm? This is an example. It's a manuscript on arXiv where we have used something called the physics-informed neural network to solve an inverse problem in this case, it's a diffusion equation in radiation belt modeling. And by doing that, we actually discovered some missing physical processes. So we actually learned some new physics. And yeah, this is my summary. The last point I want to make is that, I mentioned many examples applied to space weather. None of those examples are actually operational at SWIPSI. However, all of them or most of them claim in the paper to outperform current operational models. So in this regard, we probably still are 10 or 20 years behind the terrestrial weather. And this is, again, it's a list of all the problems I think need to be overcome in the near future. And I'll be happy to chat with you by email if you're interested in any of those topics. Thank you. Thank you.
Enrico, thank you. Very interesting presentation and a lot of commonality with our other domains. A really great way to frame the problem. So appreciate that. If the panel is ready, we have some questions queued up, which are moving up and down. Again, to those of you in the audience, if there's some question that you'd really like to see addressed, since we have limited time, be sure to upvote it and we'll kind of work our way down from the top. The first question, which has been up at the top of the board for a while, is probably most appropriate for Amy and Jason, but how can the open source movement merge with a government agency like NOAA? Will there be red tape issues? I can assure you there will be red tape issues, but how can the open source movement run with NOAA?
I would say that yes, in fact, there will be red tape issues for sure, because we as an institute agreed to a open source approach that was Creative Commons 0, which is the lowest level, the most open license. And I've had a lot of people say, how did you get private industry to sign that as an IP agreement? Google didn't complain. IBM didn't complain. The smaller companies didn't complain. You know who hasn't signed yet? I'm going to say this on the recording. NOAA.
Right.
So yes, in fact, I don't have a solution. Jason, do you have a solution idea?
So one thing, I think this is a great question. And it's very connected to the talk that Amy and I gave yesterday on partnerships and lessons learned around partnerships. One answer to the red tape is, of course, yes. That answer is yes, but it's also important to take into account the differing incentives and the differing timelines and so on of the different partners. Now, what I would say here is that this is really a clarion call for NOAA to take leadership in this area, that we need organizational leadership to guide the way forward. Now, NOAA by itself doesn't have all the expertise that's needed to develop the open science platforms. So clearly we need cooperation from cloud providers. We need cooperation from the science community. What kinds of models and what kinds of methods do we want to develop for collaborative open science? And so this needs to be a broad organization, but I think it needs to be led from within NOAA. NOAA is really a treasure house of information that drives the data science revolution. And is the clear point for creating this organization. Now, what I would suggest, what form would this take? It could look something like a cooperative institute of a different form, where we gather as a framework for the sectors coming together. On the positive side, I will say that there is organizational readiness from the private sector and academia, government. Yes. We're all unified. We want this, and we have ideas, and there's progress already developing this. We just need to come together under a common umbrella.
I would say there's organizational readiness at all levels except for the lawyers.
Well, yes. Right.
And that is the frustration.
Right. And some issues here that need to be addressed, that should be addressed, is one is IP. So where does the IP reside? I think there are many options. We operate in our institutes under the CC0 license. That's effectively public domain. So this would be entirely open. I think that model is working pretty well. The other issue is, I think, what was I going to say? I think it's around timeline. So so for the private sector, we operate on very short timescales and value agility, and that needs to also be included within this kind of vision within that umbrella. Yeah. Anything else, Eddie?
Thank you very much. Well, this next question is what I would call the AGU problem, the way I'm interpreting it. How do we improve communication and efficiency among all the sectors if we want to make real progress and not get bogged down by meeting overload? So you've all presented lots about AI, ML, appropriate to climate and to oceans and to space weather. It's great that we're here doing this, but if we don't want to have a meeting every week to share our ideas, how do you guys see communication happening so that we can share our pattern recognition and image tools across the different domains?
I have one answer. I'm going to push our new journal because that will be one answer, right? There's a brand new journal that AMS is coming out with. I'm the editor-in-chief. For those who don't know, it's AI for the Earth Sciences. And we will be accepting submissions within the next few weeks. At some point, AMS is getting it up and running very quickly. And I think that will help improve the communication efficiency without meetings, because it's another way to look at the publications. So that's one answer. I'm sure there are others. I'm just giving that as an answer because I really want people to submit and to make this new journal a big success and help improve the science across all of what we're doing.
And I have another perspective on this. First of all, David, John, this is a really hard question. So I appreciate it. So I think we're all faced with this challenge, even as it exists with too much time in meetings. Well, I would suggest that if we are constructing partnerships, multi-sector partnerships, that this be as informal as possible. So that one of the things that takes time, meeting time, is formalized meeting schedules that can potentially turn into obligations, right? So the way that we work within an organization is we meet in a flexible way according to what it is that we're trying to tackle and when the time is appropriate. And when we create multi-sector partnerships, when we're involved in multi-sector partnerships, we want that same sort of informality. Hey, I'm working on this problem. Let's brainstorm. Let's just call it up. So we need mechanisms to encourage this informality and also be very clear on the intellectual property so that we don't get stuck in a situation where we're not sure whether we can talk about something or not. And that's, again, another reason to support open IP arrangements.
I would say that a lot of these broad multi-sector collaborative projects really do require a lot of communication. And so one thing to think about is, your AI project needs to have some sort of project manager. Someone needs to herd the cats and keep that communication flow. I think that's actually a really critical part to the success that I've had in the past is being able to bring everyone together and keep those lines of communications appropriately open.
Mm-hmm. Enrico, any thoughts?
No, I would second what Amy said. I mean, I wasn't even aware of that journal, to be honest, so that's good news. But I think publication, I mean, my experience is that, it takes time to be up to date to publications, but because there's overload of that. There's overload of meetings, there's an overload of papers. But that's really the key, and that's what when I start working, for instance, with a postdoc or a PhD student, I always say, take your time, take a couple of months, 3 months, whatever it takes, and do a literature review and just understand what is the state of the art, because you don't want to reinvent the wheel. So and because of the publish or perish paradigm, and because we are always in a rush, we tend, especially I guess the more senior people, to not have time, to not dedicate enough time on staying up to date with publications. But that is, that is old-fashioned, if you like, but it's the only way to know what is going on, with your colleagues, other than, of course, the conferences and such.
Thank you.
I might add one more, which is that this NOAA conference is fabulous, but maybe we should coordinate with AMS, so that the AMS AI conference, so that we don't have meeting overload, everything due at once. I know it wasn't your fault, Eric, for example, that all the deadlines ended up this week, but maybe we should coordinate, because that does contribute to meeting overload.
Like I can say, as an organizer, finding even a week to put this without stepping on 10 other conferences was really, really difficult. So let's go on to the next question, as we have a few more minutes here. What do you see as the most important first steps towards open science platform vision? Where do we start laying the groundwork now so we can get there in 10 years?
I would say the first is to reach a collective clarity and consensus. How are we going to do that? One option, I don't know if Amy's journal might be the appropriate place, but we could, through this workshop or through some venue, collect the community under this topic. Create a workshop or a special issue around open science. So to gather the community together so that we can discuss and we can reach collective consensus. In parallel with that, as I say, I think there's a call for NOAA to lead, to show leadership in this area. So we need to start developing the structures around creating that kind of leadership, and we should be targeting 2022. It should be in the near-term future. So larger organizations will take more time to establish, but I think we need to reach that consensus and establish the beginning platforms of that coordination.
I would add one thing to that was happening in the Slack chat yesterday after one of the talks, of having a discussion of making a plan right after Peter's talk. When Peter showed the 5-year plan and the milestones and the road marks and all of that, we need to do something similar across sectors as well for the U.S. Just not just NOAA. I know the AI, the NOAA AI Center is working on it, but it needs to be sort of broad vision, and I think that will help get us going as well.
Can I add a point here? So I think it's important to realize that the funding agencies are very well aware of this issue, and they're pushing. Again, I'm more maybe on the AGU side of things than AMS, but for instance, NASA now require, I don't know if for any given grant, but typically requires the products to be open science or accessible to some extent. AGU journals now, I mean, you can't publish a paper if you don't make the code and the data accessible. So it's really going towards the direction. I mean, there's no way that can be avoided now, whether it takes 1, 2, or 5 years, I'm not sure, but just want to make the point that both the funding agency and the society like AGU or AMS, I think, are pushing in the right direction.
Yeah, that's a really good point, Enrico. I think, we want to head more towards standards that support easy collaboration. So we all publish our code. That's great. It's in different forms. It's not quite interchangeable. It's hard to take my model and give it to Amy and have her run it on her platform. She doesn't have the data. It's a different code base. So we want to support the opportunity for unified platforms. We're not going to lock people into that, of course, but we want the opportunity to have those common roles. But I take your point. We're on the road to this.
All right, thank you. Let's see, we may have time for probably just one more question, so I'll use moderator's prerogative and pick a favorite here. Christin talked about the Twitter-based whale ID tool. This seems like a powerful way to introduce and engage the public with an AI application. Can the panel members think of other domains where a similar idea could be developed? What are kind of the fun, interesting tools that we can get out there to engage the public around AI? Particularly important as we're trying to push this forward as an initiative in NOAA.
I think there's already some tools out there for doing things like plant ID and stuff. So why not, weather ID? Why not clouds? Why not, I'll let Christin answer all the other things. Sorry, I didn't mean to answer at the same time. I thought clouds are a nice, easy one, right? People often look up and say, what's that? Isn't that cool? Right? And you could get them really engaged. You could also do better crowdsourcing of your weather observations. Here's my piece of hail. How big is it actually, and where, what's the mechanism behind it? Things like that.
And
yeah, that's actually what I was going to say is the crowdsourcing platform Zooniverse has really had a lot of success in connecting, just general public to annotate data to then feed into machine learning. So I think that's been the most successful public engagement tool in this sector that I've seen.
I would add to that. So I think crowdsourced and citizens data is wonderful. So there are many opportunities here. I will also add to that, we should be, as a community, we should be very careful ethically that we have an ethical platform on which we operate, because when we introduce personally identifiable information, we introduce issues for exploitation. So we need to be very clear about what data we can collect, what the value is, who's going to use it, and so on. And so this needs to be clarified. But the opportunity is wonderful if we have that clarity.
Okay, Enrico, anything to add before I pass it over to Douglas?
No, I mean, yeah, I was going to mention Zooniverse also. There have been a few cases where Zooniverse has been used for labeling space weather data, like solar sunspot and things like that. And then also machine learning competition, I think, are a good way to engage, data scientists. That's, of course, takes more thinking. They're harder to organize, but I think we're going to have more and more of those in the future.
Yeah, that's a great point. I think we've had some success in that, and it is a way to engage the public. Thank you to all our panelists. Really great session. I'm going to pass it over to Douglas for some closeout information.
Thanks, Eric, and thanks for all the panelists who joined us for another great panel session. And Amy already beat me to it, that I'm just going to announce that the two special collections that we're going to do for this workshop, we are working together with other agencies and journals to release two special collections on open access journals. So all the work will be shared publicly and open access without paywall. The first one is with Environmental Data Science. That's a journal published by Cambridge University Press. And the other one is with Artificial Intelligence for the Earth Systems. That is where Amy is the editor-in-chief. And both journals have the guest editor from the workshop planning committee. So all the presenters of this workshop are invited to submit these two collections, and they're complementary. They're not competing with each other. So pick one that you want to submit, and we will be happy to work with you to make your work open access to the public. And the other reminder that, again, our conversation will go on in the Slack. So we have already shared some links to the journal as to other information that I have mentioned in this panel. And in today, we have another poster session at 4 p.m. Mountain Time. Again, tomorrow morning, we have our final poster session at 8:30 Mountain Time. Please join us. We have a lot of great conversation in the poster walks. And Friday, we have 3 sessions. That's one is specifically focused on integrated interdisciplinary AI development, talking about who we should invite in this process to make the AI development useful and equitable for the society. And the second session is on the Hackathon Showcase, where we'll highlight some hackathon results from before this workshop, as well as a hackathon that NOAA HPCC program ran earlier in collaboration with NVIDIA. And last session, the closing session for the workshop, we're focusing on the diversity of the workforce. So how we ensure the diversity of AI development workforce to make sure that everything is equitable and responsible. So we hope to see many of you in tomorrow's session, as well as there's also a scientific session today. So don't forget, take a bio break and join us in those sessions. Thank you very much.